Hello there students, Dr. Shruggy here, and I want to walk you through how Project 1 is going to work. I've actually divided Project 1 up into 5 pieces to make it a little bit more manageable for you. The basic problem is this. I want you to think about yourself as like you're brought in as a consultant on a project. Here's a solar panel that's going in. What is the optimal orientation for this panel? I mean, when I say optimal, what I'm talking about here is I want to know what produces the most power over the course of a year. Power might be a poor choice of a word. Maybe energy is a better idea. And by orientation, I mean what are the azimuth angles and elevation angles that will produce that maximum amount of power, for that vector that's normal to the plane of the panel there. When I say this panel, what I mean is specifically at that location, the latitude and longitude and time zone and all that kind of stuff at that particular location. What we are not going to be worrying about is going to be stuff like the efficiency of the panel. That's an engineering issue. It might be more accurate to say that we're not measuring the amount of power the panel is producing so much as the amount of power incident upon the panel, and then let engineers worry about how efficiently it's converting that into electricity. We're not going to be worrying about anything like, but the panel's out for maintenance or something like that, or any human-related things like that. And we're not going to be worrying about clouds. We're going to be assuming that all these days the panel is in sunny conditions. All day, every day is clear. Now, that's an interesting assumption, and that's actually what goes on in discussion 3 for this module. And I will let you figure out why we can go ahead and make these calculations, assuming that there are no clouds. So let me tell you how Project 1A is going to work. The first part. The first part, I'm giving you the position of the sun in the sky. I'm saying I'm going to specify a particular local elevation angle for the sun and a local azimuth angle for the sun. And then I'm going to tell you, here's the orientation of the panel. The azimuth angle and the elevation angle of the panel are fixed. And I'm also giving you the Julian day. You need to know the Julian day because there's a Julian day in the calculation of S, the flux of radiation at the top of the Earth's atmosphere. Remember that S is a function of things like the solar constant and where you are in the orbit and stuff like that. There's a little equation in one of your PowerPoints about that. Given that information, I want you to compute the flux of incident solar radiation on that panel. Now, you're going to write this as an octave program. It's not going to be particularly large. I'll talk to you about how big of a program it is in just a little bit, but a good question is, how will you know if your panel is working? Well, I tell you here, tested with the values for Evansville. Actually, I copied this slide from a different part in the presentation. There's nothing about Evansville in this part, unlike some of the other questions you'll be working with. But you're going to be given the panel's elevation and the sun angle, the sun elevation and all that kind of stuff. And from that information, you should get a flux of 1,033 watts per square meter. Now the question is, what do you do if you don't get that value? What's going on? Well, first off, it's entirely possible I have made a mistake, but I'm pretty sure this part of my project is working just fine. I also provide you on the blue line page about breaking Project 1 down into manageable steps. On Part 1A, I actually provide you with some of the intermediate values that I used to get to the final answer here. Things like, what did I get for S, the flux of radiation at the top of the atmosphere? What did I get for T atmos, the transmissivity of the atmosphere on that day? And what did I get for zeta, the angular separation between the position of the sun and the orientation of the panel? I give you those, and then you can use DISP in Octave to display your values of those parameters and see what happens. If you're getting the same values, okay, that part's working. If you're getting different values, okay, something there is wrong. So this will help you start narrowing this down. How bad is this part of the project? Well, I took a look at my program, and I, as one should, had some white space, some blank lines separating different parts of my program. I had comments that took up lines and so on. But if you stripped all that kind of stuff out and just left in lines that were doing something, my program here was 22 lines long. And if you actually go to the manageable steps page on Blue Line for this module, you'll see that I actually give you quite a bit of what you do in this particular part of the project. So I don't think 22 lines is just too terrible. I think we can make this work. Now, for each of these 5 parts of the program, the project, there's a deliverable. I want you to submit to me something so I can tell where you are on the project here. And for Project 1A, what I want is for you to use Turnitin to actually submit your program, your MATLAB, your Octave program to me. And also email me what you got for that instantaneous flux. I mean, your answer better be 1033. But anyway, that way kind of I know when you did it and so on. Alright, let me know if you have any questions. Get Project 1A working and then take on Project 1B, which is in the next video.